It is not working. Classroom 2, 2.5. No internet secured. Hey, which network is working?
Classroom 2,
But it says no internet. All right, all of you are done. So we have done the predictions. Let us see what will be our predictive probability if we submit onto the site. So I didn't write them into file, right? So we have to write them into file. PD dot data frame NB season predict dot 2 underscore CSV NB season dot CSV. PD dot data frame NB H1N1 pred dot 2 underscore CSV NB H1N1 dot CSV. Okay, so we have written them into CSV files. Okay, open the sample submission, open with Excel, Control C, Control V. NB season.csv, open with Excel, reduce to 2 decimal, Control C, Control V, Control S. Make new submission, choose file, NB, NABAS, 0.8023. Better than our logistic regression model. Better than our logistic regression model, NABAS is a better fit model, 0.80. Because categorical variables, no? We have a lot of categorical variables in our data. So this model works well with categorical variables. You guys want to submit? Yeah, please submit. I'll wait. So predict underscore proba. Predict underscore proba will give the probabilities. Choose the probabilities for 1. Okay. Reduce the decimal to 2. Okay. Select the column. The dots will be there. Reduce it to 2. Or you can directly submit the one with the full day. మీరు మెడిసిన్స్ చేసుకోవాలి ఐడియా ఉంది కదా ఫైల్ చూస్ చేసుకుంటారుగా మెడిసిన్స్ చేసుకోవాలి మెడిసిన్స్ we will take for 1 because we want to know who is vaccinated. No, 1 means yes. The thing we are predicting is objective is vaccination. Who is taking vaccination? That means vaccination yes. Yes is 1, 0 is no. So you'll copy the probabilities of 1. Because we are bothered about people who are taking the vaccination. So 1 is the area of interest. So we will take the probability of 1. Who are taking vaccinations? That is the object of the study. Who are taking vaccination? That is the object of the study. See why they are asking for probabilities. It is based on evaluation metric is ROC curve. For ROC curve, you need the probabilities to calculate false positive rate and true positive rate. AOC curve or the ROC curve. That is where we need probabilities. If you are worried about accuracy, we need classes 0 and 1. That's all. The primary evaluation metric here is ROC, AOC area under the curve. That is why we need probabilities. Got it? All of you submitted. All right. Can we move forward? So name based is a probability based algorithm which we have implemented on this data, where most of the variables are categorical in nature. So if you want, we applied decision tree? No, right? Okay, shall we move to the next set of the algorithm? Within the machine learning, within the supervised learning, we have something called support vector machines. Support vector machines, also called as SVMs. Vector arithmetic is the basis of this algorithm. Vectors or vector arithmetic. If you are from engineering background, you might have studied the vector arithmetic, right? Vectors and vector arithmetic. So vector is a two-dimensional, two-dimensional array. It uses both trigonometry and vector calculus for analyzing the data, for calculating. One of the most important calculation is the dot product calculation. In vector arithmetics, the one which is relevant to machine learning and data science is the dot product. Dot product of two vectors is this. Vector A multiplied by vector B. The arrow symbol indicates vector. Vector A multiplied by vector B is equal to AX into BX plus AY into BY. Or vector A to vector B is equal to AX plus BX plus AY by BY plus AZ plus. The resulting vector can range in the magnitude of what we call magnitude of A multiplied by magnitude of B. The lines indicate magnitude. They are not absolute. They indicate magnitude. Magnitude of A and magnitude of B. So if you are looking at the dot product formula using trigonometry, the formula is the magnitude of, the vector A multiplied by vector B is equal to magnitude of A into magnitude of B multiplied by cos theta. if theta is the angle between the vectors. If theta is the angle between the vectors, the formula is magnitude of A multiplied by magnitude of B into cos theta, dot product. So this is the fundamental of what we call as support vector machines. So support vector machines use this dot product for calculation. So support vector algorithm is both what we call as a classification algorithm as well as a regression algorithm. So if you look at this diagram, we have two types of classes, circles and squares. That means two classes in our dependent variable, circles and classes. The algorithm will draw a straight line between these two classes. This we call it as maximum margin hyperplane. Now a line can be drawn like this, a line can be drawn like this. There are different ways of drawing a straight line separating both the classes. There are different ways of drawing a straight line or separating both the classes. But the algorithm draws a straight line in such a manner that the margin between the two classes is maximum. Straight line is drawn between two classes in such a manner that the margin between the classes will be. Then two support vectors, the dotted lines are drawn touching the nearest values of both the classes. Support vectors are the dotted lines which are drawn touching the nearest observations on the both sides of the classes. Right? You can see here, right? This is the nearest thing, so it is touching this one. So this square is the nearest, so it is touching this one. So a maximum hyperplane is drawn in between, separating the two classes with maximum margin. Then two support vectors are drawn touching the closest observations on both the sides. The objective here is to maximize the width between the classes. The algorithm wants to create maximum width between the classes such that the predictions are easy to be. So this is the context of support vector machines. A straight line is drawn in between the two classes such that the margin is maximum. We call it as maximum margin hyperplane. Then two support vectors are drawn touching the closest observations to the maximum hyperplane. We call them as support vectors. Right side of the maximum hyperplane is positive class. Left side of the maximum hyperplane is negative hyperplane. 0 and 1. So this is the fundamental of support vector machine. Support vector machines is based on vector. See, in linear SVM, there are two types of support vector machines, linear SVM and non-linear SVM. So this is a example of linear SVM where the two classes are very distinctly apart. In a case of linear SVM, the classes will be distinctly apart. Now, you can draw lines like this, right? You can draw a brown line separating classes. You can draw a green line separating the classes. But which one is the best line here? The green line is the better one because it is separating with the maximum margin. So once it has done, then it will draw two support vectors such that it will separate both the classes in maximum margin. This is the linear problem. If your data is distinctly apart means there is no overlapping in classes. Then we can use linear SVM. But in reality, we can't, the data will not be linear. In textbook data, we talk about linearity, right? But in reality, it is all about non-linear. So in non-linear, a straight line cannot be drawn. In a non-linear data, this is a non-linear data where you cannot draw a straight line. Can we draw a straight line here? We cannot draw a. So in case of non-linear data, we need to convert the dimensionality of the data. We need to convert the dimension of the data from 2D to 3D. We have to convert the dimensionality of the data. Now, if you convert the dimensionality of the data, now you can separate, right? You can draw a straight line. See, we have created a third dimension using the formula z is equal to x square plus y square. Now, you can now draw a straight line in this non-linear pattern. So, by converting the linear data into, non-linear data into three-dimensional data, generally a plane is two-dimensional. But in non-linear data, we have to make the data into three dimensions. We have to create a third dimension. And then using the third dimension, we will draw a line which is in the circular form, form. So because we can't draw a straight line here, we have to in two-dimensional you have a y-axis and you have a x-axis. In a three-dimensional you have x, y, or into a four-quadrant thing. Now you can draw a line separating the classes. Now this process of converting data from linear format to a hyperdimensional format, we have certain functions that we use. We use certain functions that will help us to convert the data from a two-dimensional data to a multiple dimensional data. One of the popular functions we use is radial basis function. So we call this as kernel trick. We call this as a kernel trick. See, this is linear data where you can draw a perfect straight line. But in non-linear scenarios, this is a non-linear data. You can't draw a straight line here, right? If you draw a straight line like this, there will be misclassifications. That means you have to convert this two-dimensional into a three-dimensional hyperplane. Once you create a three-dimensional hyperplane, then you can draw a decision surface or you can draw a linear. Now, to do this thing, the kernels are very important. One of the kernel is polynomial kernel. One of the kernel which is there is polynomial kernel. K into x, y is x transpose y plus 1 to the power of d is the number of dimensions. The next is the RBF kernel, radial basis kernel, also called as Gaussian kernel. This is an infinite number of dimensions in the face. This kernel is used. Here, e to the power of minus, what is that one? What is that symbol? Not lambda. Gamma modulus x minus y whole square. Magnitude of x minus y whole square, where gamma is greater than 0. The RBF kernel is the one which we need to use when your data is non-linear in format. You can use polynomial kernel. You can also use radial basis kernel. So within the support vector machines, for linear data is drawn both the classes maximum and is called two support vectors are drawn. Two support vectors are drawn. Observations, the maximum margin hyperplane closest to the maximum margin hyperplane of maximum margin hyperplane is positive and left side of maximum margin hyperplane is negative. That is what we found for a linear. This is a linear example. This is your linear. Now, how does it do the calculation? So you can see here, right? It starts from the 0. Vectors always start from the 0. This vector is for positive hyperplane. This vector is for negative hyperplane. X plus minus x thing is into weight. Weight is the weight vector which is an orthogonal to the decision boundary. You have an orthogonal weight vector to the decision boundary. This is the weight vector. This is the derivation. The final thing you need to understand is 2 divided by magnitude of W will be the optional weight. This is the one. The objective is to maximize the width. 2 divided by magnitude of W. This is the objective of the support vector. So here, if you look at this one, support vectors, D1 is equal to weight transpose X plus B is equal to 1. W transpose X minus B is equal to 0. If it is equal to 1, positive plus 1 is a positive hyperplane, minus 1 is negative hyperplane. Weight transpose multiplied by X plus B. What is the straight line equation? Y is equal to AX plus. So just look at this, then you will understand the concept of the support vector machines. So if W transpose into X plus B is positive, that will be classified on the positive hyperplane. If it is negative, it will be classified onto the negative hyperplane. Now in non-linear, we have to map it to a higher dimensional space by using these kernels. You have Gaussian RBF kernel, sigmoid kernel, and polynomial kernel. If your data is non-linear, we have to use these kernels. For non-linear data, dimensionality has to be using the popular polynomial Gaussian RBF, polynomial, and you have to convert the data into the higher dimension using these by default is RBF. In Python and R, by default is RBF. And remember, real-time data is always non-linear in nature. Linear data is a hypothetical. Linearity of data is hypothetical situation. See, demand curves. You might have studied in economics in college and high school, right? Demand. We always take demand as straight line, right? Demand is always taken as straight line, downward straight line. Supply also we take it as straight line. But in reality, it doesn't happen. Reality, demand will be a non-straight line curve. It's a non-linear demand curve. Similarly, supply is also a non-linear supply curve. So linearity is a hypothetical. Most of the time, real-time data will be non-linear in nature, and we need to implement a kernel to convert the data to a higher dimensional space such that we can draw a maximum margin hyperplane between the classes. Okay. Now, the most popular and default kernel is RBF. Gaussian RBF kernel is the default. Now, what it will do is, when I say transformation into higher, each observation will be transformed using this formula. Like you remember density curve, where observations are converted into standard density scores using that Gaussian distribution formula. This is also Gaussian distribution formula only. If you look at it closely, 2 by sigma square e to the power of. Only thing is the magnitude is the addition here. If you look at our normal Gaussian distribution formula, it also starts with e to the power of and does the value x minus mean. There we use x minus mean divided by 2 sigma square. Here it is slightly different. It is x vector minus orthogonal weight vector or weight vector divided by 2 sigma square. And this is magnitude, not absolute. So there is a slight difference, right? If you look at our Gaussian distribution, where when we talk about your Gaussian distribution in density curve, right? See, this is the Gaussian distribution formula. 1 by sigma 2 pi e to the power of minus 1. Now, this is what we are using in Gaussian RBF kernel. We are not using this component. This component we are using in Gaussian RBF kernel. E to the power of 2 sigma square. Here, instead of x minus mean, we have x vector minus weight vector. And instead of square, we use magnitude. Right. This is the conversion of your normal observations into density scores. And then we draw a line of the density scores. We get the density curve. Remember, histogram, box plot, and density curve. Right. Density curve is done based on density scores calculated using this. Similarly, in support vector, for changing the dimensionality, we use the Gaussian RBF. The Gaussian RBF kernel is used. Now, why it is used? It is best used for separating non-linearly separable data. If your data has lot of dimensions, it means many features are there. Dimensions means features. In a higher dimension data, that means when you have large amount of features, then support vector machines are good. Suitable for small training data set with higher dimension. Generally, we don't prefer more variables and less observations, right? We want more observations and less. If you have more variables and less observations, we call it as high dimensional data. When I say, I told you now, for regression, minimum 20 observations for classification, minimum 50 observations per variable. That is the minimum requirement. If somehow this requirement is not matched, then the data becomes high dimensional data. If rows are less and variables are high, then it becomes a high dimensional data. Typically, what we do in high dimensional data is we have to reduce the number of variables using an algorithm called principal component analysis. We will talk about it. Principal component analysis is an algorithm that we use to reduce the dimensions of variables. It does not delete variables. It combines them into components. The algorithm does not delete variables. It combines them into components, grouping the variables into components based on a covariance matrix, based on similarities. Based on similarities, it will combine the variables into components. If you don't want to implement PCA, still want to use machine learning algorithm, then SVM is a best fit algorithm. SVM is best fit when you have high dimensional. Again, this also suffers from overfitting. This also has a overfitting problem, but very rarely we see overfitting problem, because what happens is in support vectors, we don't see when you have very high dimensional data, then only the overfitting problem will happen. When you have very high dimensions or many variables in your data, then only you have overfitting problem. Generally, we don't see that scenario. That's why overfitting is not that common in SVM. Whereas in decision tree, it is most frequent. In decision tree, overfitting by default happens because the tree structures are very large and they analyze the data in a better way, they tend to overfit. But in case of SVM, overfitting happens when the dimensions are many in the data. When I say dimensions, I mean to say independent variables, number of independent. Computational cost is highly intense because you have conversion formulas is there. Na? RBF will take time because you have to calculate standard deviations, vector calculus and all are there. So computational intensity is slightly higher. Computational intensity is slightly higher. Decision trees are very easy to calculate, right? See, tree-based models are very easy to calculate. So magnitude or length of vector is written as this. The formula is this: x1 square plus x2 square till xn square. The direction of vector x, x1, x2 is written as w and is defined as w is equal to x1 by magnitude of x, x2 divided by magnitude of x. So the formula of magnitude of x is this: x1 square plus x2 square plus till xn square. So the direction can also be written as cos theta comma cos alpha, and alpha and theta are the angles for the vector. And then we have the dot product. Vector x and vector y is magnitude of, these are two vectors, x and y. The angle is theta. Magnitude of x multiplied by magnitude of y multiplied by cos theta will give you the dot product. So in classification problem, if it is positive, positive hyperplane. If it is negative, it will be on the negative hyperplane. In classification, if the w into x plus b is greater than or equal to 0, it is positive hyperplane. W into x, weight into x plus b is less than 0, it will be a negative hyperplane. Okay, so this is the mathematical formulas behind the calculation of this. See, calculating this is a little bit complicated. That's why we can't do it in Excel also, because the calculations are quite complex. It is to be done using geometrical softwares. Not our Excel will not support that. Okay, so but the mathematics is behind this. It is purely based on vector arithmetics. Dot product is the fundamental, and it depends on the dot product calculations to classify the observations. Whatever predictions you are giving, if it is positive, positive hyperplane. If the value is negative, it will be given on to the negative hyperplane. Now, if you look at the support vector machines in Python, so we have SVC, support vector classifier, new SVC, and linear SVC. So all these three are both binary as well as multi-class classification. So SVC will work on binary classification as well as multinomial classification. That means more than two. SVC and new SVC are similar methods. SVC and new SVC are similar methods. Linear SVC is where we assume linearity between the observations and the dependent variable. Now, SVC is non-linear. SVC is non-linear. So if you look at this SVC, the default kernel is, because in non-linear data, first thing is you need to convert the data into a multi-dimensional data. Then only you can implement a support vector classifier. Without converting the data into a higher dimensional space using the RBF kernel, you cannot implement SVC. Support vector classifier, SVC, C support vector classification is what you call the basic classifier using support vector algorithm for non-linear data. If you believe your data is linear, then you will use linear or you will use linear SVC. But when you look at multivariate data and multivariate data, it will be always non-linear. So the best thing is we have to use SVC, which is your support vector. Now you can see you can give kernels: linear, poly, RBF, and sigmoid. The three which are most important are this: polynomial, RBF, and sigmoid. If you are using polynomial, default D is 3. Polynomial has to the power of D, right? That is, default is 3. The degree is valid only if you are using polynomial. Otherwise, if you are using RBF, the D is not valid. So, if you look at SVC, this is a classification algorithm for non-linear data. If you want to do regression, SVR, support vector regression. So, support vector machine is both a regression algorithm as well as a classification algorithm. But its performance is far better on classification problems, not that great on regression problems. This algorithm is most preferably used for classification problems, even though it can be used for regression problem. The performance on regression problems compared to the algorithms, other algorithms will be not poor. SVC is predominantly used in image processing. The first algorithm which was widely used in image processing was support vector classifier. Later we got deep learning algorithms and all. But if you are looking at a machine learning alternative, the one of the best algorithm would be support vector classifier, because images are non-linear data. Pixels, once you convert the images to pixels, it becomes a non-linear data. Typically, pixels range from 0 to 255 for a two-dimensional image. For a three-dimensional image, it will be even higher. 0 to 255 is the pixel size for two-dimensional. So once you give the image, you have to break it into numbers called pixels. Pixels are non-linear in. So support vector machines or support vector classifiers were initially the preferred algorithms for processing the images. Even now the baseline algorithm would be a support vector classifier. SVC is very good in image processing because pixel data is non-linear in nature. Pixels 0 to 255. Once we start working on images, I will show you how to convert the image into numbers, because algorithms cannot process image, right? Algorithms will process numbers. That means images have to be broken down into numbers. That process we call it as pixelization, right? And pixels will be ranging from 0 to 255. 0 to 255 based on the RGB. You know, right? Red, green, and blue RGB scale. Okay. So this is the understanding of your support vector machines or support vector classifiers, SVC or SVR. Both a regression algorithm as well as a classification algorithm. Both regression and classification and performance is good in high dimension data. And images are all high dimension data. Images will be high dimension data by default. You have 100 images only, right? That means your rows will be 100 only. But when you convert it into pixels, it will be very, very large. So images are considered as high dimension. And that is why support vector classifier has a good performance in that. See, this limitation is computationally intensive. And its performance on a low dimension data is not that good. If you have lesser dimensions, it's not that. So you guys will take a break. It's 11 o'clock and then we'll meet afterwards and implement this algorithm. So regression, this is the one. So a margin of tolerance is set in approximation to the SVM. A tolerance limit will be set. So these are the constraints. Y minus weight x minus b less than equal to epsilon. Wxy plus b minus ya less than equal to epsilon. In classification, we call it as margin. Here it is epsilon. Now epsilon value you have to get. No, it is epsilon. 2 by magnitude of width. 2 divided by magnitude of width. The formula is 2 divided by magnitude of width. See, epsilon by default is 0.1. That means 10% above and below the hyperplane. Right? By default is 0.10. It specifies the epsilon tube within which no penalty is associated with the training loss. It must be non-negative. So you can define your epsilon 10%, 20%. 0.1 means 10%. So observations plus or minus 10%, you will draw a line. Right, predicted values plus or minus 10%, you draw a line. Plus 10 minus 10. Errors. That is error. If everything falls into the epsilon boundary, you will not have errors, right? See, what is epsilon says? Where there is no penalty associated with the training loss. That means if the residuals are falling or the predicted values are falling in that narrow range, then they are assumed as correct predictions, right? If they are falling outside this, they will be considered as errors. So in case of classification, we use the word margin. In this, we have the epsilon. Epsilon is the tube type of things. Plus or minus 10% is the default epsilon in Python. This is not for variables. This is for predicted values based on the calculation. No, once see. No, it's not range. We should first find the predicted value. How will you find the predicted value? Using the equation which we are generating. That what is that equation we are using here is this equation, right? Wx minus b, and you will get a values here greater than or less than equal to epsilon. Once these predicted values are calculated, they will be put into plotted as the scatter plot. And once you have the scatter plot plotted, then you will draw the epsilon rates. 10% lines will be drawn. And anything falls above or below that will be considered as errors. See, it's vectors, na? All the values are considered as one vector. So each variable, one vector. And each vector will have weight. Weights like coefficients calculated here. We will assume certain weights. So it is sigma weight into vector. And then you will get the final value. And then the predicted values will be plotted into scatter plot. And then a narrow range of 10% plus or minus will be drawn on the average of the predictions. We'll take the average of the predictions, right? And then you draw a 10% plus or minus 10 to that one. And anything that falls out of the boundaries will be considered as wrong predictions or errors. So we'll implement 77.90. So for 82.12 for imbalanced data, you have to do value counts.
0 and 1, you see the graph. We plot the bar graph and it's kilometer per liter and there's only practical.
For numerical data, there is no imbalance. Imbalance is native to classification data only. For numerical data, we have other problems, now skewness, outliers, and kurtosis. So classification only has imbalance problem. For regression, we have other problems called skewness, outliers, and kurtosis. So we'll write the predictions. See what is the impact. So we have not predicted, right? Sorry. Is equal to SVM model dot predict underscore proba vaccine. Why we got another here? Probability is equal to true. We have to give. So PD dot data frame season is the problem. 0.8214. Build decision tree classifier on this data and see decision tree classifier. Or there is something called stacked ensembling, stacking classifier, where you can specify multiple models, build multiple models at once. So look at this code. Random forest, linear SVC, logistic regression, stacking classifier. Estimators is equal to RF, random forest, estimators, SVR, make pipeline standard scalar, linear SVC. You can define multiple models and then you give your final comparative estimator and then you can give the, so multiple models will be built and then you will also get the best fit model. Similarly, stacking regression is also there, where you can build multiple models in one go and finalize which is the best fit model. Try this. Import logistic regression, decision tree, random forest, GBM, give estimators as a list. So you have to create a list of estimators from sklearn.tree, decision tree classifier, from sklearn.ensemble, random forest, from sklearn.ensemble, gradient boosting classifier. Rest of them we have, right? So we have to also from sklearn.ensemble stacking classifier. Estimators is equal to square bracket and within round braces. So you can see here within round braces, you have to give the name of the model, short name of the model like this, comma, decision tree classifier, comma, random forest classifier. So this is only with two brackets. Boosting classifier, categorical NB, SVM, comma, SV. These are the models, right? Tree, RF, GBM, NBM, NBN, SVM as estimators. CLF is equal to stacking classifier, estimators is equal to estimators, comma, final underscore estimator is equal to logistic regression. CLF model is equal to CLF dot fit X, comma. By default, we'll take, na? Or you can add it. By default is how much? 100, na? As an additional argument. CLF model for X, comma, Y. 84.C. Logistic regression is predicting better. That's what I'm checking. You have named estimators. This is CLF model dot final estimator. This CLF model dot final estimator. CLF model estimators. So we'll get the best model accuracy only. So this is the process of CLF. In R we get the each model score, but here we are not getting it. In R we get each model score separately. Baseline estimator. So that is what we have done now. Baseline estimator is there now. The final estimator which is used for prediction is that is the best model. Logistic regression is the best model. Third for reception में दे दो. Reception ले change. Comparative estimator, base estimator. You have to have a comparative estimator, right? So in this case, the final estimator is the classifier which predicts the given the output of estimator. So whatever is the best is the final estimator. We have given multiple models, right? So in this case, logistic regression is the best fit model. Comparative estimator we gave, na? Final estimator comparison is logistic regression. See, there are two final estimators. The final estimator in the top parameters is this. In parameter, what you give as final estimator is this one. What is this? A classifier will be used to combine the base estimators. The default classifier is logistic regression. It is used to combine all the base estimators. Whatever list we are giving, all the predictions will be combined based on that one. By default is logistic regression. In the output, final estimator means something else. In the output, attributes means output. In the output, the final estimator is the classifier which predicts given the output of estimators. Based on the estimator's output, it identifies the best estimator. That will be your final estimator that will be used for prediction. So final estimator in when you're giving as parameter is different. Final estimator we are getting as output is different. They are not same. In this case, it was same because the best fitting model is also logistic regression. So there are two different things. Look at the documentation. All models will be built. All models will be built. Whatever you are specifying, all models will be built. See, this is what it is saying. All models will be built and the score of all models will be taken. And among that, which one has the highest accuracy, that will be your final model. That is the process of stacking. Stacking means you build multiple models, identify the best fit model, and use that best fit model to prediction. That is the process of stacking. You build multiple models at a single point of time. Individually, instead of building individually model by model, you build all the models in one iteration and find out which is the best fit model based on the accuracy score, and that will be your final best fit. This process we call it as stacking the output of individual estimator and use a classifier to compute the final prediction. So all the models will be built, all the models accuracies will be taken, compared, and whichever model has the highest accuracy, that will be your best fit model that will be used for prediction. In this case, logistic regression is the best fit model. So stacking is where you can build multiple models in one single function, and then you will get the best fit model. So just read the documentation. So this is the process. See here, model 1, model 2, model 3, all the models, all the values, predictions will be estimated into one place, and then the second level model will use the predictions and the final prediction will be done. This is the process of stacking. See here, same data, different models. See here, same data, different algorithms, KNN, decision tree, SVM, and each model's prediction will go out into the final one for each observation. So model 1 is KNN is predicting it as, for the same observation, decision tree is predicting it as broccoli. For the same observation, SVM is prediction as broccoli. The final prediction of that observation would be same observation, what logistic regression is predicting, what data science is, data decision tree is predicting, what random forest is predicting. All these things will be taken, majority voting will be done, and that is your final answer. So this is the process. Same data, different algorithms. For every observation, each algorithm will give its prediction, right? Like in this case, KNN is predicting it as grape. These two are predicting it as broccoli for the same observation. Final answer would be broccoli. This process, we call it as stacking. So all the predictions of all the algorithms will be taken into one place and majority voting will be done. Whatever is the majority voting, that will be the final answer. In case of regression, average. In case of regression, it will take the average of all predictions. That will be the final prediction of the stacked model. So here, this is the process of stacking. Bagging is sampling method here. Don't get confused. That is a sampling method. What sampling we are doing here? Don't get confused between concepts. Bagging is a sampling method. Are we doing any sampling here? No, we are doing a stacking. Stacking means one upon the other. And then you take the stack, find the best, and make it as your best possible prediction. So there is no sampling here. So it is the output of the algorithms that we are voting upon. The output of the algorithms are being voted upon, not the models. What each algorithm predicts for each observation, that will be aggregated and that will be sent to the final prediction. Now, is this clear? Regression is average. Suppose KNN predicted the value as 2,800. This has predicted the value as 3,100. This has predicted the value as 3,600. So it will take 2,800, 3,100 plus 3,000 divided by 3. That will be your final prediction. So stacking is used. We are doing it individually, right? What we are doing, we are building model after model, and then we are comparing the outputs, results, and then we are doing it. In stacking, you do it all in one go. So when you go into advanced machine learning, where if you don't have time for doing individual model and all, you want to do all models in one go and do it, you can use the stacking model. Now, earlier we used to use a small code for doing it. Now Python has integrated it as a part of it. But I would not suggest to do it because you will not get individual model scores here. So you will not get individual model scores. You will not get individual metrics like precision, recall, F1 scores. Then how will you can make a decision, right? So this is, as we go ahead in data science, we call this as auto ML. In Azure and all, we can do this. Azure, AWS, and GCP, where you click on the model boxes and give the input data, it will do it all and give you the final metrics in a form of a dashboard, and which is the best fit model. That comes under auto ML, automated ML. Okay. Now, a lot of people are talking about automated ML. There will be no role, but automated ML is costly. Automated ML is costly. See, bringing data to X and Y is the biggest challenge, right? That system cannot do. As of now, pre-processing system cannot do. After pre-processing, if you have clean data, you can use auto ML. You can run all sorts of models. It will run all the models available and give you the best fit model. But IBM and all Google are also have auto ML where they do automatically data pre-processing also. But that requires a lot of computing power. So Google has developed a model for missing value imputation. It tries all methods, most with that simple imputer, KNN imputer, probabilistic imputer, your mice imputers, neural network imputer, all the imputers it will try, and then it will come up with the best missing value. Now, for this to happen, it will take hours, and it requires a lot of computing power, right? Whereas we manually can do 1 or 2 imputers, and we can analyze those 2 imputers and do it. But when you are doing it, you can do all sorts of imputers, but computing is very, very costly. Now, despite after doing all these things, will it be 100% accurate? Because there is nothing called 100% in statistics. Stacking is to understand. Like, in what you call in Kaggle and all, there is a different types of stacking. You build a model, you will take weightages. I'll take 30% of the decision tree model, 20% of the random forest model, 10% of the Google one. I'll create a new prediction. That is also a process of stacking, manual stacking method. You calculate probabilities. Whichever model is giving you the best probability, that you allocate more weightage. Whichever model is giving you less probability, you allocate 30 to 100, 0 to 100%, and you calculate the final value. And then you can, you expect it to have a better accuracy in this thing. You will see such sort of ensembling in Kaggle house price prediction. Such sort of ensembling you will see in Kaggle house price prediction. If you remember the Kaggle prediction, some people do it. But what I personally found was that works sometimes, that doesn't. So if you look at the code files, see, this guy used stacking model plus Yo Johnson. Now, what he did was, he did all the pre-processing and all the stuff. Then he built these models. Okay. He built linear regression, random forest, support vector regression, light GBM, parameter tuning for light GBM, ensemble regressor. Now he is combining. See, like how we use stacking classifier, he is using stacking regressor. Final estimator is LR, linear regression. Okay. And then he fit it and he calculated the working with test data. Also, he did all the pre-processing what you have done in the trained data. So he implemented the model on the test data also. And finally, he got all the models. I think random forest was the best fit model. SVM score is 84.3. Light GBM is giving negative. So finally, he went with random forest. Okay. So let us see if we find any stacking model. Pipeline ensemble models. So he created a function for evaluate model. He created a function for base CV result, and he listed all the models. See, linear regression, SVR, all these things, and then he ran all the models. So if you see here, he created a applicate function, evaluate model, model.fit, x train, y train, model.predict, x value, and written a RMLSE. RMLSE means root mean square error. For that also, he has created a function. Y true, y predict, right? Mean square log error. He created a base result, CV1, and he ran all the models. He went to elastic net, regularization methods. We will support vector regressor with different kernels. random forest with different estimators. One model with 100 trees, 200 trees. So he is doing with different estimators. And he finally found out that 700 is the best fit model. So grid search algorithm has been implemented, and then he is ensembling the results, voting regressor. So all these models are used, and then all the outputs of the models will be combined, and then a final prediction will be generated. So the basic idea is when you do such process, you will get a slightly better accurate prediction. That is the basic understanding. Experience is it's not the case. It is always better to build the models individually, understand the impact of variables, and then build the model. Stackings maybe you might use later when you have experience in data science, but initially it is always better to understand the parameters. You have to understand accuracy, precision, recall, F1 scores. In case of classification, all these metrics have to be analyzed, balance, imbalance, everything. Then only you will come up with the best fit. Whereas the stacking guys will give you this one. So I will, part of syllabus, we will give you this voting regressors, stacking regressors and all. But it is always better to, now grid search, we will talk about it in the next session when we talk about the k-nearest neighbors. Grid search means you build, there is this grid search where you can give different models, like one random forest model with 100 trees. If you look at here, one random forest model with 200 trees, one random forest model with 300 trees, one random forest model with 400. So like that, he gave 100 to even max depth also, he has given between 1 to 11. Okay. And then he did the what you call grid search. Now, after doing all this, building all these models with 100, 200, 300, 400 trees, the grid search summary will give you the best fit model. What was the model that has the highest accuracy? Then you can finalize your trees. We are now taking randomly, right? In grid search, you can give whatever values you want. It will build all the models and it will finalize the best fit model. That is called grid search. Grid searching is widely used when you don't have a fixed formula to find the value. It will build all the models. So grid search, we'll do it in the next class where we will implement KN. We will stop it here and we'll continue in the next session.